Hello, everyone. Welcome back. This is lesson 5 of Machine Learning Zoomcamp session 4. And in this lesson, we will talk about ROC curves. ROC stands for Receiver Operating Characteristics, and this is a way of describing the performance of a binary classification model. Originally, this idea was used during Second World War for evaluating the strength of radar detectors. So let's say we have a radar. So we have a radar, and then there is a plane. Right, and the radar wants to detect a plane. This is also kind of a machine learning problem. So we can think of y equals 1 that the plane is there, or y equals 0 that the plane is not there. And the features in this case are the signals from the radar. Right? So from the signals of the radar, we want to understand if there is a plane flying over a radar or not. First time, ROC curves were used for this problem. And for that, we are interested in two things. We're interested in two numbers. So first number is false positive rate. And another thing we're interested in is true positive rate. Both these metrics are computed from the values of the confusion matrix. So let's quickly draw it. And then for the confusion matrix, again, we have our predictions. So here we have positive prediction, we have negative prediction. Positive could be that, okay, user is churning or the radar detected a plane. Then we have actual values. So again, we have positive and negative. And so you remember that this is y equals 1 and this is y equals 0. And for this one, it's our model makes a positive prediction or our model makes a negative prediction. So here we have true positive, we have true negative, then we have false positive, and we have false negative. So now let's go back to this false positive rate and true positive rate. So false positive rate is the fraction of false positives among all positive examples. So for this one, we are interested in this part, in the first row. So we look at all negative examples, all the examples that are actually negative. So all the users who didn't churn. And for them, so what we're interested in is the fraction of false positives. So this is false positive divided by the total number of examples here. So it's true negative plus false positive. So we're interested in this number divided by the total number of negatives. Right? And in the same way, for true positive rate, we're interested in the second row of our confusion matrix. It's very similar to false positive rate. So we're interested in fraction of true positives over the total number of positive examples. So it's false negative plus true positive. So again, we're interested in fraction of observation in this cell, in the true positive cell, divided by the total number of true positives. And if we think about that in terms of ovals, let's draw this oval. Here we divide our customers into positive and negative ones. So these are non-churning ones and these are churning ones. So let me just split it a little bit. So, okay, now I kind of separated them. And then here we have, again, this division. So here we have true positive and we have false positive. And yeah, so here we have true negative. And here the last one is we have false negatives. For true positive rate, we're interested in fraction of true positives over total number of positives. This one gives us true positive rate. And then for false positive rates, we're interested in fraction of false positives over the total number of negative examples. So this is our false positive rate. Okay, and here for false positives, we want to make it as low as possible. So we want this part with false positives be as small as possible. And so we want this true negative part to take as much space here as possible. So we want to minimize the number of false positives. And in the same way for true positive rate, we want to make it as big as possible, right? So we want to expand it as much as possible. And we want to minimize the false negative part, right? So we want to minimize false positive rate and maximize true positive rate. ROC curves are based on these two values. So let's quickly compute them. So first we have true positive rate, which is a number of true positives divided by true positive plus false negative, right? Right, and then false positive rate is number of false positives divided by the number of false positives plus true negative. Right, so we have false positive rate. And you probably notice that for true positive rate, it's the same as recall. So if we print our recall here, it's the same, exactly the same value. It's exactly the same value as the recall. And false positive rate, yeah, we haven't looked at this before, but we want it to be as small as possible. So here, 9%, or it's almost 10%, means that for all the negative examples, 10% are still predicted incorrectly. Okay, we have these values, these two values, but what we actually need and what ROC curve is good for is instead of evaluating these two values just for one threshold. So for this case, we evaluated them for this threshold of 0.5, and we got these two values. ROC curve looks at all the possible thresholds. So for each threshold that we can think of, it evaluates these qualities, and then we plot them. So you'll see how we will plot them, but first let's actually compute them for all possible thresholds. So again, for that, we'll use the linspace function, linspace. And let's say we can have 101 of them. So then for t in thresholds, what we need to do is we want to evaluate these values here. So we want to get the confusion table. So let's move it here. So now we have these predictions, and here we remove t because we don't want to evaluate it on a fixed threshold. We want to actually iterate over different thresholds. Then next one is, let me just copy it in one go. So here we have that. So we have that. Of course, if we execute, nothing happens because we just compute these values and throw them away. Now let's put all these values into a data frame. And then from this data frame, we can compute this true positive rate, false positive rate, and all these things. So I'll just create a variable called scores. And then for this scores, I'll append a tuple. So the tuple will contain the threshold for which we evaluate our model, and it will contain all these values: true positive, false positive, false negative, and true negative. Now scores looks like that. So you see, this is a bunch of tuples, and then we have a lot of threshold. Right? So we move with increments of 0.01. And then for each of the threshold, we evaluate all these values for the confusion matrix. So we end up with 101 different confusion matrices evaluated for different thresholds. So what we want to do now is we want to turn it into a data frame. And we do it this way. So we put it inside pandas. We put a list of tuples, and then pandas creates a data frame like that. Of course, it doesn't know about the columns. What column names are there? So we need to tell it. So let's say columns. Now we have threshold, and then we have, so just copy it here. Now we just specify columns here. So we have that. Let's take a look at what we actually have inside. So we have the same content as we saw previously. Now it's a data frame. Maybe what we can do is look at each 10th record using this column 10 operator. So this tells to print every record from the very first record till the last record, move with increments of 10. So this is what we do here. So we actually have 11 records here, and then for each, we see the values for the confusion table. Now let's compute true positive rate and false positive rate. So we have our formulas here. So true positive rate is this one. False positive rates is the rate is this one, and then we just need to add this df scores in front of each. Now, of course, we need to do it this way. Okay, now let's take a look. So again, we'll look at each 10th record. So now we have these values, true positive rate and false positive rate here. And what we can do now is we can plot them. So let's plot them. So first we have our thresholds. And then, yeah, first let's plot the true positive rate. And then let's do the same, but with false positive rate. So to make it easier, let's add the legend to know what each line represents. So label, this is true positive rate, and this label false positive rate. And then we also need to add legend. Yeah, so the blue one is true positive rate, the orange one is false positive rate. So on the x-axis, we have a threshold. Right, and for threshold of 0, so we see that both true positive rate and false positive rate are 1. So it means that for this, and this is a dummy model that predicts everyone as churning, right? So for them, true positive rate is 100% because for all the positive customers, for all the churning customers, all of them are identified correctly. And again, false positive rate is 100%. For non-churning ones, we make 100%. So we predict all of them incorrectly as churning. And then we see that it goes down. So the blue one and red, so they go down with a different rate. The orange one goes down faster. And actually we want to go down. We want it to go down as fast as possible. So remember, we want to minimize it. So we want this value to be as low as possible. And for true positive rate, of course, we want to keep it around 1. Yeah, so now we actually can get some ideas for the performance of our classifier. So we can see this for different values. And yeah, probably we can get some ideas that for our threshold 0.5, we can see how many mistakes of each type we make. But still, just looking at this graph, at this plot, doesn't give us enough insights because we don't have anything to compare it against. So what we want to do now is actually have this baseline. So for us, it will be a random model. So a model that for each customer basically flips a coin and thinks, okay, this customer is churning, this customer is not churning, and just making decisions whether this customer is going to churn or not completely randomly. So let's implement that. We can just assign every customer a random score between 0 and 1. And that we can do with this random package. We want to have a uniform. We want to draw from the uniform distribution. The size should be the same as our validation data set. So this is how our predictions look like. Just in case we can fix the random seed. I don't think it's important here. Let's fix the random seed. So these are the values we get. These are the values we get. So yeah, basically for each customer, just randomly predict if they are going to churn or not. So accuracy for this model should be quite low. So let's say if we use 0.5 threshold to want to compare it with our Y, so we can see that the accuracy for this model is 50%, which is expected. So in 50% of the cases, it just by luck got it correctly, but for the others, yeah, it didn't. So this is the model we have, and now we want to plot the same values true positive rate and for false positive rate for this random model. So for that, let's just take all the code we wrote here and put this in a function. And this way we can just pass any predictions here and then get a data frame. So I'll create here TPR, FPR data frame. So here we have actual values, then we have the predictions. Okay, that here, and then we need to create a data frame and also compute this true positive rate and false positive rate. So let me copy it here. Yeah, so what we need to return at the end is this data frame. So we have this function, and we can use now this function for getting that data frame with random predictions. So let's call it random, and then for y, for the actual values, we'll still use the values from our validation data set. And then here we use the random predictions. And here, let's take a look at this. Every 10th record, we see that true positive rate and false positive rate, it decreases. So basically with each when threshold moves by 0.1, it also moves kind of by 0.1. We can see that if we plot, so let me just copy the code for plotting. So if I replace now this TF scores with TF random, we'll see that both of them go down. It's a straight line, almost a straight line from 0.1 for threshold of 0 to 0 threshold of 1. So let's take a look again at a few thresholds here. So let's say for 0.6, it's 0.4 for both true positive rate and false positive rate. And the reason for that is basically because we're here almost like throwing a coin, but this coin, because we are here looking at threshold of 0.6. So this is our threshold, 0.6. So in 60% of cases, this model predicts that this customer is non-churning. And in 40% of cases, it predicts that this customer is churning. And we see that's why it's 0.4, which is 40%. So just with probability of 40% for a customer that is churning, it predicts that it's churning. So that's why we have 40%. And with probability of 60%, it predicts that this customer is non-churning, which means that in 40% of the cases, this model is incorrect for non-churning ones. So yeah, we have this, it's almost a straight line from 1 to 0. Now let's talk about a different benchmark. So for this one, we want to talk about the ideal model. So model that outputs the correct prediction for everyone. For this case, for case of ROC curves, we want to consider an ideal scoring model. Suppose we have a bunch of customers. And for each customer, we have predictions, right? So let me just copy it. And let's say we have some predictions. So for example, the customer here, we have 0.3, then 0.5, 0.1, 0.8, 0.5, and so on. So we have these predictions. What we want to do is we now want to take all these predictions and then order them in such a way that here we have the smallest at the beginning, and here we have the largest score. So let's say in our case, the largest one could be, I don't know, 0.9. The smallest could be 0.0, and then so it's 0.01, 0.01, 0.02, somewhere in the middle, maybe 0.5, and then I don't know, 0.89. So we ordered these customers by the score, and the ideal model orders customers in such a way that first we have all the customers who are non-churning. So all these people after ordering, they are non-churning, and people after that, customers after that, all of them are churning. And let's say if for us the threshold is 72, 72% of non-churning people and 28 of churning. Right? So if we use a threshold 0.70 something, so our model will have 100% accuracy, because it will classify every non-churning customer as non-churning and every churning as churning. But it also orders them in such a way that there is a clear cut between non-churning and churning. Right? So this is the ideal model. So for this model, let me move it a bit. So for this model, so here we have the scores. So the scores are from 0 here to 1 here, right? So we go from the lowest one to the highest one. So let's implement that. So for that, we first need to know the number of negative examples, number of people who are not churning. So for that, number negative. So in our validation data set, we need to count how many zeros there. And for the positive ones, so number positive, we just need to count the number of positive examples. So we see that we have 1023 negative and 386 positive examples. And what we want to do now is we want to create something like this. First, everyone is non-churning, and then people are churning. So for that, we will create Y ideal. And in this case, first, it will contain only negative observations, and then it will contain only positive observations. For that, we'll use NP repeat function. So we want to create an array that first contains zeros and then contains ones, and then it should contain 1023 zeros, and then it should contain 386 ones. So and this is what we'll get. So the way it works, it repeats this number of times the first element from the list, and it repeats that many number of times the second argument from the list. So let's execute that. So we see that it's first zeros followed by ones. So this is kind of our validation set in a way. So we know that everything is ordered here. Now we need to create our predictions, and predictions can be just numbers between 0 and 1. So we'll use the linspace function that we want to create numbers between 0 and 1. And we want to create as many of them as there are observations in our validation data set. So this is how it looks like. So let's create Y ideal predictions. So this Y ideal predictions is the predictions for our classifier, and this Y ideal is kind of it's the actual values. So our customers who are churning or non-churning. So for this one, accuracy, so let's say if we look at the accuracy, so what was that? 0.72. So for that, and if we compare it with the ideal one, and look at the accuracy, so it's 99%. I think it should be something like that. Yeah. So let me see how many Y validation mean. One. So it should be 7 to 6. Yeah, so now it gets everything correctly. So it just predicts that for people above this threshold, they are positive, below negative, and it happens to be correct for all the clients because this is how we prepared our actual values and our predictions. So this is how ideal model looks like. Of course, this model doesn't exist in reality usually, but this helps us to benchmark our model that we have against this one. So let's do the same exercise for the ideal model as we did for the random model. So we'll take this and we'll create a data frame. Let's call it data frame ideal. And then for the actual values, we'll use Y ideal. And then for the predictions, we'll use Y ideal prediction. And then let's just quickly take a look at this data frame. So we see some values here. I think it's more interesting to plot it. So let me just plot it. So replace everything. Let's plot it. What we see on this plot is true positive rate almost always stays around 0. So this is ideal scenario. And then it starts to go down at this threshold. So this threshold is 0.72726. So this model can identify, so for true positive rate, so this model can identify the churning customers correctly. For people who are not churning, when it says they are churning, it's not always true. It becomes true when it crosses this threshold. Right? Simply because, let's say for 0.4 here, so this is false positive rate here is 45%. So it means here that it still makes mistakes simply because we cut at 0.4. So for approximately 20% of people who are predicted as non-churning, but they're simply below this threshold of 7 to 6, we predict them as churning, even though they are not. And yeah, of course, that's why the model is, we're making a mistake when we are using this threshold, and that's why the false positive rate is 45%. But of course, it goes down, and at the threshold of this threshold, it classifies everything correctly. So this is how ideal model looks like. And what we can do now is we can try to plot all our models together. So we can all the benchmarks together. So we can plot the ideal model. So we can plot the random model, the ideal model, and the actual model. So let's start with the actual one. Then we have the random one. And then we have the ideal one. So yeah, let's take a look at this. So I think for random ones, they are not really, so we can just remember that it goes from 1 to 0. So let's maybe remove them. Yeah, so we have that. And so we can have the ideal model as just change color to, I don't know, black. So I actually want to do this for the ideal model. So yeah, now they are black. So we see that if we compare our model with the ideal model, our true positive rate, we actually want to be as close as possible to this one, right? So we see that it's quite far apart. So even at the threshold of 0.5, right? So when this model has a true positive rate of 100%, so we are making quite a lot of mistakes. And likewise, this false positive rate, yeah, so it's quite far from this one. Plotting it against the threshold is not always intuitive because, for example, for this model that we have for our model, the best threshold, as we know, is 0.5, at least in terms of accuracy. But for this model, the best threshold is 7 to 6, right? So they have different thresholds. What we can do, however, is to plot false positive rate against true positive rate. So in a slightly different manner. So here, we don't plot the thresholds. We just look at only true positive rate and false positive rate. So let's plot them. So we have our scores. On the x-axis, we will have false positive rate. And then on the y-axis, we will have our true positive rate. So this is true positive rate. So this is how it looks like. To make it easier for us, let's also add the benchmarks. So we have our random model and the ideal one. We can also add labels here. So this is our model. Then here we have random, and here we have ideal. So this is how it looks like. Before I explain what's going on here, I want to make it square, because usually the ROC curves are square, not rectangular like we have here. So for that, we need to specify the size of our plot. So for that, we use this fixed size. Let's make it 6 by 6. So yeah, now it's just make it a bit smaller, 5 by 5. Yeah, so now it's squared. So what we see here is our random model. So we saw this behavior on the previous plot. So it just goes, so true positive rate and false positive rate, they move together. So that's why it's kind of straight line between 0 and 1. So there are some fluctuations here simply because this model is random. Sometimes it by chance gets a bit more accurate. Sometimes it gets a bit less accurate. That's why there are some fluctuations. And then that's also what is also interesting, the way the ideal model behaves. So let me just add labels here. So X label. So on the X-axis, we have false positive rate. And on the Y-axis, we have true positive rate. So this is a bit easier. So for the ideal model, it reaches this point when both true positive rate and false positive rate are 100%. And this is, remember, this is a threshold of 7 to 6, right? So they have a point when both of these values are 100%. And this is like the ideal spot. So we can call it the North Star. So this is where we want to get. So we don't actually need to plot the random one. So what we can do is we can just plot a line between 0 and 1. So between 0 and 1. And for the ideal one, yeah, we know how the ideal one looks like. So we don't need to plot it as well. So we know that we want to aim at this point over here. So we can just keep it in mind. So we don't need to plot it every time. Yeah, so this is how a ROC curve looks like. So for this ROC curve, we plot true positive rate against false positive rate. And we usually add this random baseline. And we want our curve to be as close as possible to this ideal spot, right? And to be as far as possible from this random baseline. So if our model is somewhere close to this baseline, then it's not a good model. So we want to be as close as possible to this ideal spot. So in this ideal spot is where we make no mistakes, right? Of course, our model makes mistakes, and that's why the ROC curve for our model looks like that. So now let's spend a bit of time trying to understand what's actually going on here, what kind of information we get from this plot. So let's say we start here with 0 false positive rate and 0 true positive rate. So this happens at bigger threshold, like let's say a threshold of 0.1. So this is where for every customer, we predict that they are non-churning. So our true positive rate is 0 because we don't predict anyone as churning. That's why it's always 0. And the false positive rate is 0 as well because there are no false positives. We only have true negatives there. So this is where we start. So we start at the threshold of 1 here, and we finish here with threshold of 0.0. So this is where our model has 100% true positive rate because we predict everyone as churning. We are able to identify all churning users, but we also make a lot of mistakes, right? So in all the cases when we say it's positive, customers are churning, those are false positives, right? So we incorrectly identify non-churning ones. So that's why we have true positive rate of 100% and false positive rate of 100% as well. So we, let's say here we have, I don't know, a threshold of, let's say 0.7. So we're slowly lowering the threshold and we start predicting more customers as churning. So we don't say that everyone is non-churning anymore. So for some of them, we say, okay, some of them are churning. Yeah, so our false positive rate starts to increase a little bit because we are making mistakes, and true positive rate also starts to increase because we are making some correct decisions. And yeah, so if you remember the ideal model, so it doesn't make any false positives. So only the true positive rate is increasing for the ideal model. Like, and for our model, so we're making some mistakes. That's why we're deviating a bit from the ideal scenario. Yeah, so we are coming a bit closer to the performance of a random model. And let's say here, threshold of 0.6. And yeah, let's say somewhere here, it's 0.5. As we move the threshold, we're predicting more customers as churning. So that's why our true positive rate increases and false positive rate also increases because we have mistakes. And for example, a good model would behave like that, perhaps. It will stay close to this ideal line. Of course, it will make some mistakes, but it will stay close. So it will stay far away from random model. So it will have a reasonably good true positive rate while still maintaining a low false positive rate. Right. And then, of course, at some point, we're starting to predict more customers as churning more than there are actually churning customers. That's why our false positive rate increases, but our true positive rate, again, for good models, it stays close to 100%. Let me just draw it quickly. This is our plot. We have here false positive rate, 100% here, and here we have true positive rate. So we have 100% here, and yeah, so this is 0. So we know that the random model looks like that, and ideal model goes like that. And as we said, a reasonably good model. So this is, let's say, this is okay model. So this is something like we have, it's okay, could be better, it's not too bad. And then quite a good model will stay very close to the ideal line. Maybe it will look something like that. So this is a good model. And then a bad model will be quite close to the random model. So this one is bad, this one is random. If for some reasons our model is getting somewhere here below, then yeah, we're making a mistake here. So models should not go here, should not go below the random baseline. If we see that our model goes below the random baseline, it means that we need to flip positive and negative predictions. And then it will become something like this. So if you see that your model goes below the random baseline, something is wrong and you have a mistake somewhere. So this is a ROC curve. So using the ROC curve, we can see how the model behaves at different thresholds. So you remember that each of these points here on our ROC curve is true positive rate and false positive rate evaluated at a particular threshold. So here can be 0.8. So here can be 0.2, 0.5 here. So we evaluate our model on different thresholds. We plot it, and then we see how far it is from the ideal spot and how far it is from the random. And this can also be used to comparing different models. So let's say we have another model that looks like that. And we see that this model is a little bit better than what we have because it's a bit closer to the ideal spot and a bit further away from the random baseline. ROC curves are quite useful on their own to see how well our model is doing. But what is more interesting is a metric that is derived from the ROC curve is called AUC, which stands for area under the curve. So for area under the curve, what we want to see is the area here, and it tells us how good our classifier is. And this is something that we will look at in the next lesson.